So the last speaker before lunch is Professor Bijaya from PRL Ahmedabad, and he's going to talk about isotope shift studies. Let us see. Okay, Bijaya.
Okay, thank you, Subhadeep. He's a very close friend of mine. So yeah, so I have already thanked those like organizers. So let me just start directly with my presentation. So the problem that I'm going to talk about, it's a very old problem. In fact, several experimentalists from India, they have already measured isotope shifts earlier. But as Kanaya was mentioning, that in some cases you will find that the experimentalists are advanced than theoreticians. So this is one of the examples. Though this is one of the old problems, but isotope shifts were measured very precisely in early days. But it was very difficult to calculate them accurately. So what I'm going to do is here I'll tell you, the problem is divided in two parts. One is the recent the developments from the theory side to get or to explain the experimental results, what we have done. Second part is the new directions we have introduced here that can motivate some of you to consider these problems and carry out these measurements and see some kind of new physics that we'll like to probe some kind of new physics beyond the standard model of particle physics, like the kind of things the person was talking about. So okay, I am from PRL. So this is the campus. I think many of you may be knowing about this. So the outline of my talk will be like this. So it will be a more or less pedagogical talk because there are many students are present. So I'll start with many times people think that when you talk about atomic spectroscopy theory, they think that if you know hydrogen atom theory, that means the how to calculate wave functions or energy levels like that. But let me tell you that what is the difficulty, why that is not, it is not that simple, and we have to deal with a lot of complicated many theories. And then what is isotope shifts? Those to whom who are not familiar with that, then we have developed, or like Prasanna was mentioning about this couple cluster theory, that is known as one of the all-order perturbative method. So I am going to talk about this methods, how we use that to calculate the wave functions accurately, hence any properties you want to evaluate later on. Then so there will be actually, even you have the methods to calculate the atomic wave functions very accurately. It doesn't mean that you can calculate the wave and properties in the same way. So there will be different approaches also. I'll like to show you some of the examples. Then what are the challenges to estimate the isotope shifts theoretically? Then some of the recent results and what are the future directions. Okay, so where is the problem in atomic theory? This one, if you want to really understand. So all of us, we know that we in quantum mechanics we have to deal with the Schrodinger equation in non-relativistic framework, or in the relativistic framework we have to consider Dirac equation, and this is the basically Hamiltonian. Now if you consider a hydrogen-like system, so you are familiar with that. So this is a kinetic energy term, and this is the the nuclear potential, and here in the relativistic framework, so this part will be replaced by these two terms. So for this kind of Hamiltonian, we know the solutions exactly, analytically we can solve. So that is why in many textbooks that it has been given. So what is the advantage, in this kind of analytical approach? So when we solve, we introduce something called this quantum numbers to describe the states. Okay, now what happens when you consider more than one electron system like helium or any other system? So we'll have this Hamiltonian will be, there will be one additional term. So that has two coordinate systems, and because of the presence of such terms, so the system becomes solving the Schrodinger or Dirac equation becomes complicated. And so this is in fact, if in the relativistic framework or non-relativistic framework, whatever you consider, actually this is not the actual atomic Hamiltonian. In fact, in the hydrogen atom also, what we are considering, that is one approximated Hamiltonian. So if you take, for example, if you consider hydrogen to deuterium or helium 3 to helium 4, or different to 3 to 23 sodium or 25 sodium like that. So then, there will be change in the energy levels, and these energy levels are known as isotope shifts. And this is what, now if you want to calculate those energy levels, so then one has to use this kind of atomic Hamiltonian. So which will be a function of nuclear mass, and then we'll have this the nuclear potential, and that also will be a function of nuclear charge radius. So you'll have with a different size of nucleus. So this potential will also vary. So this energy change, if you want to find out from one isotope to another isotope, so that is known as the isotope shift. So the idea is very simple. And like if you want to calculate energy levels for subsystems, now you have to use the relative coordinate systems, and then rho or capital R, and then generalized momenta, they are defined here. Now, if you want to translate this momenta to this electron coordinate system, then you can write down this total Hamiltonian into 4 parts. One is the nuclear Hamiltonian part. This we generally don't consider in the atomic energy level calculations, because all the atomic energy levels are actually scaled with respect to this Hn. Then this is, now we'll have these 3 extra contributions. So this was our original atomic Hamiltonian, but then we'll have 2 additional contributions. So one is known as mass shift, then another, this one is known as field shift. So mass shift means due to the change of mass, nuclear mass, you'll get slightly energy change. And this is due to the change in the size of the nucleus. So this is known as field shift. So this mass shift Hamiltonian is given by here, and this we can further divide into 2 parts. So this one is known as normal mass shift, and this is known as specific mass shift contribution. And then field shift is basically change of this nuclear potential with respect to the nuclear charge radius. Okay, so now if you want to estimate this effect theoretically, so the total energy will be the energy that we had due to the atomic Hamiltonian, and then due to this mass shift and field shift. So basically these effects are very small. So that is why we estimate them up to first order effect. And this is the scaling factor. So the normal mass shift can be written expressed in this way, and this known as normal mass shift constant, and this factor here is known as specific mass shift constant. Now, if you remember earlier, I had told you what is the challenge why we cannot solve the atomic energy levels theoretically in the multi-electron systems. That was the presence of, due to the presence of two-body operators, two-body interactions. So here, this specific mass shift operator is also another two-body interaction operator. So this, yeah. Sorry about this. Yeah, so now this makes us challenging to now if you want to estimate this isotope shifts accurately. So this is why people didn't like early days when the supercomputers are not available, or that kind of many-body methods or powerful many-body methods are not available. So that is why people are trying to get rid of this kind of effects. So why they're what they're trying to do. So now, so similarly the field shift this effect can be expressed in terms of this first order effect. You can so this is known as root change root mean square radius of nucleus. So this field shift effect also can be estimated up to first order. So with this parameter. So early days, what people are doing, so they are neglecting these effects, and so they are using an equation which is known as it's a famous equation known as King's plot. So what they are doing is they are considering 2 different type of isotopes and 2 different kind of like transitions. Then they are expressing using this expression up to considering the first order effects. So they are expressing this, they are using this relation. So then when they are trying to measure the isotope shifts into different transitions, and then they are plotting, so you can express, if you use this equation, as you see that, so this factor becomes independent of this transition frequency. So then when you plot, you will get, this will become just a slope. And then from there, you can extract this ratio of this field shift constants for 2 different isotopes. So now if you know this field shift constants, then if you substitute here this field shift constant, so this is expressed in this form. So from there you can extract the nuclear charge radius, and that is how, if you extract this value, then you can find out the nuclear charge radius for different kind of isotopes. And then they are trying to compare that with the nuclear model values, and then they are trying to probe different kind of nuclear theories. So that was the original objective of studying these isotope shifts earlier. So now let us now I'll tell you what we have now, instead of using this kind of equations, whether theoretically we can estimate the entire all these 3 quantities and then compare with the exponent value or not. So then what development we have made recently to understand that, let us try to see what kind of methods we can develop, or we have developed recently, and that we have used to estimate these quantities. So now, just to start with, so person had mentioned about this. So this atomic Hamiltonian, as I said, we can divide into two parts. One is which depends on one coordinate system, then another is two coordinate system. So this guy is the problematic for us. So what we do is, so instead of writing this, we replace this, this part into one kind of midfield potential. So then we rewrite the entire thing into parts, and then it becomes this Hamiltonian, we call atomic midfield Hamiltonian. Then this part is known as a residual interaction. So then, so this one will now become, is a single coordinate operator, and like a hydrogen atom problem, we can solve this equation. That means this part exactly, and then so the a single particle orbital wave function will be like this. So this is the approximate one can consider. But now the important is, the important point here is, so this part is not actually non-negligible. So if you are talking about high precision calculations, so this part also has to be included up to infinite order. So that is the idea. And how to do that? So if you go with a perturbation theory, you cannot deal with that. So in the perturbation theory, what we do is, okay, first thing is, I think this I'll skip that, because this is how we, how we get this Hartree-Fock orbital wave functions. Okay, now let us say that this atomic Hamiltonian, as I explained in the previous slide, so we divide into two parts. One is the mean field wave function that we are using, getting by solving the Dirac-Hartree-Fock wave function. Then we have this residual part. So now let us say this is our total wave function psi. So this psi will be divided into two parts. So this P, which is known as projection, this one or model potential, a model space of this wave function. So that is a wave function coming from, because of this Dirac or mean field wave function Hamiltonian, and the rest that we have neglected because of this corresponds to this Q space. So our idea is to include contributions from this Q space as much as possible to get the exact wave function, and that can be obtained by operating some kind of wave operators. So that means what like Prasanna was mentioning today morning. So we need to construct the all possible kind of excitation, because with respect to this, so this will become the orthogonal space, or you can express in terms of single particle excitation with respect to this P. So that means we have to include this excitation configurations with respect to this from here to get the total wave function. So this is the idea. But now the question is, this you can do in several ways. But then what kind of theory, how you will make sure that which theory is actually correct to do this kind of things. So if you want to find out that, so we have to first, there are some like many-body theory characteristics that you have to verify. For example, if we develop one theory and we divide the entire system into two parts, A and B, and when you are calculating the total energy, let us say you calculate into two parts, A and B, then if your theory is working properly, so then the total energy should behave in this manner, and the total wave function of the system should behave like that. If it is doesn't satisfy this, then that theory should be discarded, or it should not be considered as a valid theory. So the coupled cluster theory that we are using so satisfies this. And what is coupled cluster theory, I'm going to explain. So that to understand coupled cluster theory, so we can start with the perturbation theory. So in the perturbation theory, as I said, so we have mean field Hamiltonian, then this correction we want to add perturbatively. So this is the 0th order correction, then these are the higher order corrections. Okay, and energy also can be computed like this. And if you have one external potential, so then we'll have this we'll have two different kind of external potential. So they have to also included in this manner. But when you apply ordinary perturbation theory approach, we can only go up to 4th order, 5th order at the most. In fact, nobody is able to do that, but you cannot go beyond that. But our aim is to perform high precision calculations. So we want to include these perturbations up to infinite order. So for that, so what how we construct the wave function. As I said, in the perturbation theory, we'll have these two parts. So this already we get from the mean field calculation. So we need to construct, consider contributions from this part up to infinity. Now, if you see, each order is a linear combination of this, these unperturbed wave functions or excited state configurations with respect to this phi 0. So that is why we can rewrite each order in a different way. So then we'll have this kind of a single excitation configuration, double excitation configurations with respect to this, with these coefficients, which will have contributions up to infinite order in interactions. That is the idea. Sorry. And this configurations can be generated from this phi 0 using this kind of second quantization operators. In the coupled cluster theory framework, so this part we write in a slightly different way. So we put in one exponential part T, which has this form, and then if you compare, so then this will be like this is single excitation configurations. So this will take care of the double excitation configurations like that. Then then in the end it will give an exponential unjudged. So what is the if we could have considered this instead of that? Why we are considering this? There are several advantages. One is this satisfies this size extension property that I mentioned. Another thing is, let us say I cannot go on adding this Tn contribution because I will have computational limitations. So generally we take only T1 and T2. So that means if I consider here I'll have Ci and Cii, that means single excitation and double excitation. So in this way, if I put that in the exponential form, so I will have this non-linear contributions Tiq, T1, T2 products and so on, that will correspond to higher level excitations. So this is the advantage of using coupled cluster theory. Now, provided we know the coupled cluster theory, so then we can calculate the energy expression or energy of the states using this approach. But the the issue of the so we then this is the amplitude. Once we using this equation, we solve the amplitude of T operators. Then the energy can be calculated using this kind of Jacobi iterative approach. But the problem is, if you want to compute other properties. So what happens now? There are one approach is called finite field method that Prasanna was mentioning. In this approach, you add this external operator whose expectation value you want to evaluate. In the perturbative approach, introduce one lambda parameter. Then you calculate the new energy level in the presence of this external operator. Then you evaluate this change in energy up to by taking the derivative. So now, if so, this first order correction will correspond to the expectation value of this operator. But you see, in this approximation, these higher order corrections are being neglected. Okay, but sometime, so this choice of lambda will be very important. So it will depend on the energy levels that you are for which you are calculating. Second thing is the operator that you have considered here. So this is it introduces numerical instability. So now to avoid that, so we can also adopt this approach, but this approach also has a problem. Now if you see in this expression, so we'll have this numerator and denominator, there will be two non-terminating series. So this also we cannot manage. So this approach also, though people are using that, but they have to forcefully truncate this expressions and perform the calculations, and then this part I'll just leave it. So this also doesn't satisfy this Hellman-Feynman theorem. So this has several issues. So to avoid that, what we have done is we have proposed one new method recently that is known as analytical response approach. In this approach, the Hamiltonian is again written in the same way like finite field approach we had mentioned. And then the wave function of the system, we express because we are interested only to calculate the first order energy shift. So then we only have to evaluate the wave function up to first order correction. And then if you can solve this wave function, you can get this psi0 by solving the Schrodinger equation. Now our aim is to get this psi0 1. So for that we want to solve this equation. That is the idea. So now in the coupled cluster theory, so this can be done by expanding T into T0 plus lambda T1. And then this will be the expression for unperturbed wave function and first order perturbed wave function. Then if you substitute that, the expectation value expression becomes like this. So this expression avoids the non-terminating series, and it doesn't have that lambda dependency that the finite field approach and in the finite field approach we had. So this has several advantages, and so this is those points are listed here. So this we developed for the first time 2 years ago. And now with that method, so we wanted to study the isotope shift. So these are the first applications. Now from the computational point of view, if you see, so this is very simple to calculate, and people are also trying to estimate that using King's plot. So this one is little challenging because the electron correlation effects that is involved through this p square, that is the kinetic energy term, is very complicated. That means very strong. So that is why earlier when people are trying to study this isotope shifts, they are using semi-empirical formulas. Basically, virial theorem they are using. And as I had told you earlier, because of this dependence of this electron momenta toward the operators, this is a very challenging operator to deal with. And these are actually relativity expressions to calculate this normal mass shift and specific mass shift constants. So this is the like first time when we proposed this method and applied. So we applied to this indium, and then there were some measurements was going on in CERN. By combining that, we had tested this King's plot, and these were our calculations there. These are the like our estimated uncertainties. And later, last year, actually this year in the beginning, last year, so we tried to apply this method to potassium, exotic potassium nuclei, and got, so this was by combining experimental data and with our theoretical results. So these were the nuclear charge radius of potassium, and these were the values predicted by nuclear theories. So that using this one, we are trying to actually probe how so there are several nuclear theories were applied here. So then we are trying to validate which nuclear theory is more like accurate. Then we repeated that to this sodium isotope, which doesn't have many stable isotopes, and these were the results of different isotope shift constants. And here you can see that when you calculate specific mass shift constants, you would take singles and doubles or singles and doubles and triple excitations. There is a huge change in the energy, the values. Okay, so these values were estimated using experimental that King's plot, and these are from our calculations. And you can see that this if our calculations are predicting very precise results. So this is the first achievement from a theoretical side. And so even from this study, we also try to probe this nuclear structure theories. And you see that the different nuclear structure theory, we are predicting this radius in this manner. But our study shows the values should be like this. So this appeared last year we had published this these results. Now let me come to the new directions to these studies. So actually what I told you in the beginning, if you recall that how the isotope shift expressions were used experimentally. So we had used this linear this expression. It's called King's plot equation or something like that it's in the linear form of these frequencies. And but what we had neglected this second order higher correction, second order onwards, right? But if let us say the precision of measurements are improving these days because you have several new experimental techniques and you can improve this isotope shift precisions, then we can take into account these higher order contributions. Okay, but then you have to modify this equation, and after taking into account this higher order corrections or at least up to second order correction, then you can see that your measurement should follow this expression. But what has been observed recently, that there is a slightly deviation from this measurement, and that we attribute to something called new physics. And it's called like what people are saying, what people are saying, that there is a possibility that you can find some kind of new boson, and between that will give rise to an electromagnetic interaction between electrons and nucleus, and that can contribute to isotope shift in this order. And this shift is of the same order like the second order this isotope shift corrections. So if you want to prove this existence of new boson or something like that through isotope shift measurements, so in the calculations, so this second order effects also has to be included, and this is known as non-linearity, non-linear effect in the isotope shift studies. So you can so for example, there is evidence on this that is like using the clock transition in ytterbium ion. This was probed, and they had found some kind of non-linearity, and you can follow this paper to understand this problem better. And there are several other like proposal studies have been done. Evidences are like there is one new paper, it has been accepted in PRX, and this was one of the paper which was proposed the first paper where this effect was proposed. And so here also like there is evidence that calcium ion one sees such kind of nonlinearity deviation, and these are the actually new directions towards for studying isotope shift measurements in a different atomic and ionic systems. So I think some of you like Kanaya, you and Sourav, if people can consider these problems, and since people are doing hyperfine structure constant measurements, these measurements are almost similar, but you have to only replace, you have to consider different kind of isotopes in the laboratory. Yeah, so now let me come to summary. So as I said, we have developed several all-order manifolding methods to study atomic properties, and recently we have developed this finite field expectation evaluation approach, and analytical response approach to calculate the different isotopes, particular isotope shapes. And then we have studied this nuclear charge radius of several isotopes. But we still would like to, because this is the new theory we have developed, so it is easy for us to apply it to other systems and study. If some of you are interested to carry out in measurements in other systems, then we can help you. And also, like we are developing methods to further include this second order, higher order corrections in the isotope effects in the calculations. And also we need to develop many other methods to study similar properties in some other kind of systems. Because if you see the systems that we have chosen, they are like basically one valence systems. Yeah, so with this I would like to now thank and acknowledge my collaborators. So this is Ronald Garcia from MIT, and this is Vernon from CERN, and this Ben from Zurich. So these are the people who are collaborating with me for this kind of studies. So all the calculations are carried out in Bikram 100 supercomputer in PRL. And now I'd like to thank for your attention.
Questions?
Sir, can you say about that EA, X or EB? I thought I saw in a slide that when A and B, there's energy correlation and the wave function correlation you were talking about, like which kind of property they should adhere to. There was psi A cross psi B and that EA, X or EB.
Okay.
Understand that part. Can you?
Okay. Now I can actually use the board. Now you see you are calculating, this energy you want to calculate, right? So this is equal to H, and psi. Okay. So what you do is the entire system you split into two parts. So that means your wave function will be psi A. So you cannot have, because even there will be interactions among them, you cannot directly write that. You'll have like this, right? You compute it like this. You use the same many methods, but you divide it into two parts. So that means when you compute this energy, that is energy of AB, the entire system, and then you calculate AB as EA, then you calculate this EB separately. So they should behave additive properties. Almost they should be equal. So if it is not behaving, that means you are not able to include the electron correlation effects correctly. So it's known as size consistent problem in many-body methods. Like anybody is familiar with using configuration interaction method, that has this issue.
In the slide where you show the new terms, okay, hyperfine terms, that new effect you are talking.
Or new effect.
So there are a new, that is a hyperfine. Yeah, let's go back. Expression. So that is new B NP and a new A NP. These are hyperfine splitting.
No, these are isotope shift transitions.
Isotope shift, yeah. So
Isotope.
that is one is what is A and B?
What is A and B? Oh, these are two different transitions. That's what I mentioned. You consider two different transitions in two different isotopes.
Okay.
Okay, so this one transition is B, another
So
transition
now,
is
what
A.
kind of operator you are choosing here? So when you have this new physics you are talking about.
So what I said, see, earlier we are considering this, right? You are familiar with this mass shift, then field shift. This
Right.
basically we used to consider. We used to neglect these higher order effects. Okay, forget about the second order effects. Now, what happens is if there is like a new boson, which is actually many people are expecting, right? If you take beyond standard model particle physics. So let us say that will also contribute to your transitions.
So that what kind of neutral current or some kind of interaction you are talking
That's what I'm saying. It's equal kind of potential.
Equal potential.
Okay, so you will have this some potential. That means it were minus m, and that phi you will have some of the nuclear, some coefficients. So then this will have this
That means you are talking a scalar boson.
Yes, scalar boson.
Right. Okay. Fine.
I also have a question here. So when you are saying new bosons, so that is still mediating electromagnetic interaction? Or
Electromagnetic. Otherwise, you will not. If it is Hallowell's parity or something like that, then it will.
It's electromagnetic.
Electromagnetic.
One more is that when you showed that your result with the experimental results converging, did you check your convergence in the theory?
Sorry?
Your theoretic numerical convergence.
This is a numerical convergence.
No, you showed it. Yeah, this one.
This one, you see.
Yeah.
So because you experimentally cannot verify, because this has only two stable isotopes, you cannot verify. So you go with only higher order corrections. You know, first we perform the calculations in singles and doubles. The next higher order is you have to include triples. Then next order will be quadruple. But that way, that limitation we have, this one. So.
Okay.
if you have tried to see whether this new calculation method, how does it work for the data that has been published, for instance, from the Vuletic group regarding the ytterbium measurement? You showed one plot, and then recently
this is what I'm trying to do. See, I can directly do the isotope shift this one.
Right.
But the thing is, now if I want to probe this new physics,
Mhm.
so I have to also develop, I have to extend my, that method to include this higher order correction.
I see.
Without that, so I'm working on that because this is very recent work. I
Right.
started working on 2020.
Right.
So last year also we had 2-3 publications.
Right.
Now this year I'm extending that method because as you see, no student is involved in developing such methods. So it is taking little time, but it will be done in 1 or 2 days, years it will be done.
Right. So typically when you are doing this King's plot kind of measurements, you ideally want an element which has multiple isotopes and which has multiple narrow transitions which can be measured
That
with.
was the actual earlier objective. But
Right.
what actually, if you see in this paper, what we have tried to probe, see here the idea is to understand the nuclear structure.
I see.
So there, what they are considering is a radioactive potassium, nuclei, because it's basically, looking at this, they have, some kind of behavior that, and they are not able to explain that in using nuclear physics theory.
Okay.
And that's why they are, trying to focus in this region, because
see.
they have seen that if you take neutron number around 32, they see some kind of double magic wavelength and like that, and that they want to.
Okay. I
But
see.
if you take other isotopes, these things are understood. Like you see that the theory and experiment are matching,
Mhm.
but in this region it's not matching.
Right. No, because I think one of the objectives of doing this clock measurements is to study
These days, all the clock experiments are being diverted to this.
to do this. Yes,
So
exactly.
ytterbium ion, now this is the result for ytterbium ion.
Yeah.
And now we are proposing how to do this using CD plus, CD ion, microwave, this one.
Okay.
We are writing a paper on that.
Okay.
And so those things are now, clock transitions are, because you need a similar kind of precision measurement.
True.
So that is why
Can you comment like what kind of shift would be like a Hertz level or
Hertz
sub-Hertz
level on. That's why I said clock, this one.
sub-Hertz level?
Yeah. So this, what you see, the contribution from here, it will be at the Hertz level.
Okay.
But
Thank you.
Yeah.
think about it. I
Yeah,
think
thanks. Like this is something new. I think both of us can think of
Yeah, definitely. We should talk. Yes.
and also I think Sourav, since you are doing hyperfine structure constant measurements, this can be also another problem.
Then let us thank Bijaya.
Okay, thank you.